Take a moment and picture this: a glass of lemon juice, a dash of vinegar, and a beaker of hydrochloric acid in a chemistry lab. They might differ in strength, purpose, and safety, but they all share one powerful trait. They're acids. Now flip the scene. You've got soapy water, a dab of toothpaste, and a vial of sodium hydroxide. Different again, but each one is a base. So, what's the invisible thread connecting all acids? And what makes all bases behave the way they do? In this video, we'll reveal the hidden identity shared by every acid and every base. And here's a hint. It all begins with water. Let's step into the lab. You add hydrochloric acid to a test tube containing zinc granules and bubbles form. What's that gas? It's hydrogen. Now try the same with sulfuric acid or even acetic acid, and again, you get hydrogen gas. Clearly, there's something all acids have in common, and that something is the hydrogen ion, written as H. But here's the catch: H ions don't exist alone. They're highly reactive. So when an acid is dissolved in water, these H ions latch onto water molecules to form hydronium ions, written as HO. Let's look at hydrochloric acid as an example. Hydrochloric acid dissolves in water and forms HCl plus HO plus Cl spelled out. Hydrochloric acid plus water produce hydronium ion and chloride ion. And guess what? These H or HO, spelled out H plus ion or H3O plus ions, are exactly what carry electric current in acidic solutions. Try this experiment. Connect a bulb to a solution of hydrochloric acid. It lights up. Now do the same with glucose or alcohol. No glow. Why? Because while they contain hydrogen atoms, they don't release free H ions in solution. That's the defining trait of an acid, not just hydrogen, but the power to release H in water. Let's turn our attention to bases. What do sodium hydroxide, potassium hydroxide, and even something as mild as lime water have in common? It's the hydroxide ion, written as OH. When a base dissolves in water, it releases these OH ions, and that's what gives bases their characteristic traits. They feel slippery, taste bitter, and turn red litmus blue. Let's look at the dissociation process. Now H Na plus or spelled out, sodium hydroxide breaks into sodium ion and hydroxide ion in water. Similarly, KOHK plus or spelled out, potassium hydroxide breaks into potassium ion and hydroxide ion AMG, or AMG superscript 2 plus 2 or spelled out, magnesium hydroxide breaks into magnesium ion and hydroxide ion. So whether it's a strong base like potassium hydroxide or a weak one like AMG, or the defining feature is the release of hydroxide ions in solution. Here's something important: not all bases dissolve in water. Only those that do are called alkalis, like sodium hydroxide and potassium hydroxide. So next time you see a cleaning agent or test a solution with litmus, remember, if it's producing OH ions, it's a base. Here's a fascinating fact. Dry acids and bases don't act acidic or basic at all. Let's see it in action. Take dry hydrogen chloride gas and pass it over dry blue litmus paper. Surprisingly, no color change. Now dissolve that same gas in water, and instantly, the litmus turns red. What changed? Water. It allows HCl to ionize, releasing H plus ions that give acids their properties. The same rule applies to bases. Sodium hydroxide releases hydroxide ions, but only when it dissolves in water. So, water isn't just a background player, it's the key that unlocks the behavior of both acids and bases. And here's a safety tip. Mixing strong acids or bases with water releases a lot of heat. That's called an exothermic reaction. Always add acid to water slowly, not the other way around. Or you could get a dangerous splash. Let's test your understanding with a quick challenge. Which of the following solutions will conduct electricity? A. Glucose solution. B. Sodium hydroxide solution. C. Hydrochloric acid solution. D. Alcohol solution. Take a second. What do you think? The correct answers are B and C. Why? Because sodium hydroxide releases OH ions and hydrochloric acid releases H+ ions, both in water. These free ions make the solution capable of conducting electricity. But what about glucose and alcohol? Even though they contain hydrogen atoms, they don't break apart into ions, so no current flows through their solutions. Want proof? Set up a simple conductivity test. Dip the electrodes into each solution. Only the real acid and base will light up the bulb. This simple test shows us the real difference. It's not just about having hydrogen, but about releasing mobile ions in water. The science of acids and bases isn't just for labs. It's woven into your daily life. Feeling a burning sensation in your stomach? That's your body producing too much hydrochloric acid, or HCl. To get relief, you take an antacid, a mild base that neutralizes excess H+ ions and soothes acidity. Ever wonder why toothpaste is slightly basic? It's designed to neutralize the acids produced by food and bacteria in your mouth, protecting your teeth from decay. Soap works because it's alkaline. It reacts with acidic grime and oils, breaking them down and helping you wash them away. In industries, when acid spills happen, workers immediately apply a base like slaked lime to neutralize and contain the damage. And in the atmosphere, sulfur dioxide from factories mixes with rainwater, forming acid rain. It corrodes buildings, damages crops, and threatens aquatic life by lowering the pH of rivers and lakes. So, whether it's a tube of toothpaste or a thunderstorm overhead, you're constantly surrounded by acid-base interactions, often invisible but always at work. Let's bring it all together. All acids release H+ ions in water and often form H3O+, the hydronium ion. All bases release OH ions when dissolved in water. These properties only appear in aqueous solutions. Water is essential. Just having hydrogen in a molecule doesn't make it acidic. It must ionize. And yes, only these free ions let electricity flow through the solution. So whether it's vinegar on your salad or sulfuric acid in the lab, it's not just the chemical, it's the ions that matter. Chemistry isn't just about naming substances. It's about understanding what they do, especially in water. Join us in the next video as we uncover the strength of acids and bases and see how the mysterious pH scale reveals their true power.